Hi, and welcome to this review of the sum and difference trigonometric identities. We have a lot of useful formulas to cover in this video, so let's get started. Before we dive in, let's take a moment to review the unit circle. The unit circle gives you the sine and cosine values for some of the most common angle measures. With this information combined with some of the formulas we're going to cover today, we can find the exact trigonometric values of even more angles on the unit circle, all without using a calculator. Let's start with the sum identities. The first one we'll use is the formula for finding the sine of the sum of two angles. Let's look at the formula. The sine of the sum of the angles alpha and beta is equal to the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. So if we want to find the sine of 75 degrees, we can do this by finding two angles that add up to 75 and using them as alpha and beta. Fortunately, that's easy to find on our unit circle. Since 30 plus 45 equals 75, we can use 30 as alpha and 45 as beta. We could also use 45 as alpha and 30 as beta. It doesn't really matter. First, let's write down the information we need for our two angles. We're using 30 degrees as alpha, so we're going to write down alpha equals 30 degrees. And then we'll look up our cosine and our sine values from our unit circle. So the cosine of 30 degrees is equal to the square root of 3 over 2. And the sine of 30 degrees is equal to 1/2. Then we do the same thing for beta, which we've set as 45 degrees. So beta is equal to 45 degrees. The cosine of 45 degrees is equal to the square root of 2 over 2. And the sine of 45 degrees is also equal to the square root of 2 over 2. Now we'll write down our formula for the sine sum identity. So the sine sum identity says that the sine of alpha plus beta is equal to the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. Then we'll substitute 30 degrees for alpha, 45 degrees for beta, and then substitute all of our sine and cosine values into the right side of our formula. So the sine of alpha plus beta is the sine of 30 degrees plus 45 degrees. Then we have the sine of alpha is 30 degrees, times the cosine of 45 degrees, plus the cosine of 30 degrees, times the sine of 45 degrees. Then we're going to substitute in our sine and cosine values. So we have the sine of 30 degrees plus 45 degrees is 75 degrees, which is what we were looking for, is equal to the sine of 30 degrees, which is 1/2, times the cosine of 45 degrees, which is the square root of 2 over 2, plus the cosine of 30 degrees, which is the square root of 3 over 2, times the sine of 45 degrees, which is the square root of 2 over 2. Now we're going to simplify with a little bit of multiplication. So 1/2 times the square root of 2 over 2 is the square root of 2 over 4, plus the square root of 3 over 2 times the square root of 2 over 2 is equal to the square root of 6 over 4. And finally, because both terms have the same denominator, we can write our answer as a single fraction. So we'll get the square root of 2 plus the square root of 6 over 4. As you can see, it's important to be strong in handling radicals and fractions to do this kind of work. We can check our answer by using a calculator. If we add the square root of 2 to the square root of 6 and then divide by 4, we'll get approximately 0.966. If we then use a calculator to find the sine of 75 degrees, we get the same thing. But that begs the question, why don't we just use a calculator to find the sine instead of doing all this work? The answer is that the calculator is giving us an approximate value of the sine of 75 degrees. If we want to know the exact value, we need to do it the long way. When taking a standardized test, if you see the word exact in reference to a problem like this, then you'll know how to do this process. What if we want to find the exact value of the cosine of 75 degrees? We have a sum identity formula for that too. The cosine of the sum of the angles alpha and beta is equal to the cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta. It works in a similar way. We can plug in our values and find the cosine pretty quickly. So we're going to start by writing down our cosine sum identity. It's really easy to mix up the values if you don't do this, so it's always a good idea. So our cosine sum identity says that the cosine of alpha plus beta is equal to the cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta. Then we'll substitute 30 degrees for alpha, 45 degrees for beta, and then substitute all of our sine and cosine values into the right side of the formula, just like we did with the last problem. So we have the cosine of alpha plus beta, so 30 degrees plus 45 degrees, equals the cosine of alpha, so the cosine of 30 degrees, times the cosine of beta, so the cosine of 45 degrees, minus the sine of alpha, which is 30 degrees, times the sine of beta, which is 45 degrees. Then we'll plug in our sine and cosine values. So first we'll simplify this left side and get 30 degrees plus 45 degrees is 75 degrees, so the cosine of 75 degrees, which is what we're looking for, equals the cosine of 30 degrees is the square root of 3 over 2, and the cosine of 45 degrees is the square root of 2 over 2, minus the sine of 30 degrees is 1/2, times the sine of 45 degrees is the square root of 2 over 2. Once again, we do some multiplication and write our answer as a single fraction. So we have the square root of 3 times the square root of 2 is the square root of 6, over 2 times 2 is 4, minus 1 times the square root of 2 is the square root of 2, over 2 times 2 is 4, and we can simplify this to one fraction and get the square root of 6 minus the square root of 2 over 4. Just like the last problem, we can check our work by evaluating this radical expression on a calculator and then finding the approximate value of the cosine of 75 degrees on the calculator. It matches up, so we did something right. There's also a sum identity for tangent. The tangent of alpha plus beta is equal to the tangent of alpha plus the tangent of beta over 1 minus the tangent of alpha times the tangent of beta. Let's use this identity to answer this question. What is the exact value of the tangent of 75 degrees? In order to figure this out, we need to find the tangent of 30 degrees and the tangent of 45 degrees. But that information isn't on our unit circle. Fortunately, we can find it easily enough because we know that the tangent of alpha is equal to the sine of alpha over the cosine of alpha. We could do that twice for each of the two angles we need and then plug it into the sum identity for tangent. But since we just found the exact values for the sine and cosine of 75 degrees by using the sum identities for both sine and cosine, we can plug those answers directly into the simpler identity to find our answer. So remember, the sine of 75 degrees was equal to the square root of 2 plus the square root of 6 over 4. And the cosine of 75 degrees was equal to the square root of 6 minus the square root of 2 over 4. So now we're going to write out our tangent identity. We know that the tangent of alpha is equal to the sine of alpha over the cosine of alpha. So if we want to know the tangent of 75 degrees, we simply plug in the sine of 75 degrees, which is equal to the square root of 2 plus the square root of 6 over 4, and then divide it by the cosine of 75 degrees, which is equal to the square root of 6 minus the square root of 2 over 4. Now to simplify this, we can rewrite this as division of fractions. So this would be the square root of 2 plus the square root of 6 over 4 divided by the square root of 6 minus the square root of 2 over 4. Now remember, when we divide fractions, we flip the second fraction and multiply them. So this will be equal to the square root of 2 plus the square root of 6 over 4 times 4 over the square root of 6 minus the square root of 2. Now we can multiply these together and our 4's will cancel out. And we'll be left with the square root of 2 plus the square root of 6 over the square root of 6 minus the square root of 2. If we didn't know the sine and cosine of 75 degrees, it would make sense to use our sum identity for tangent. So let's walk through what that would look like. As usual, we start by writing down all the information we're going to need. In this case, we have to use the fact that tangent is equal to sine over cosine to find our values for the tangent of 30 degrees and the tangent of 45 degrees. So we're going to say that alpha is equal to 30 degrees, and we need to find the tangent of 30 degrees. We do this by dividing the sine of 30 degrees, which is 1/2, by the cosine of 30 degrees, which is the square root of 3 over 2. This simplifies to 1 over the square root of 3, and then this will simplify even further to the square root of 3 over 3. This comes from rationalizing the denominator, which is something we'll cover a little bit more later on in this video. Now let's find beta. Beta is equal to 45 degrees. The tangent of 45 degrees is equal to the sine of 45 degrees, which is the square root of 2 over 2, over the cosine of 45 degrees, which is also the square root of 2 over 2, and this is equal to 1. Next, we write out our tangent sum identity. The tangent of alpha plus beta is equal to the tangent of alpha plus the tangent of beta over 1 minus the tangent of alpha times the tangent of beta. Then we'll substitute 30 degrees for alpha, 45 degrees for beta, and then substitute all of our tangent values into our formula. So the tangent of alpha plus beta is the tangent of 30 degrees plus 45 degrees. This is equal to the tangent of 30 degrees plus the tangent of 45 degrees over 1 minus the tangent of 30 degrees times the tangent of 45 degrees. Now let's plug in our tangent values. So first we're going to simplify the left side over here. 30 degrees plus 45 degrees is 75 degrees, so we're finding the tangent of 75 degrees, which is what we want. The tangent of 30 degrees is the square root of 3 over 3, plus the tangent of 45 degrees, which is 1, over 1 minus the tangent of 30 degrees, which is the square root of 3 over 3, times the tangent of 45 degrees, which is 1. So this is equal to the square root of 3 over 3 plus 3 over 3 over 1 minus the square root of 3 over 3. Our numerator will simplify to the square root of 3 plus 3 over 3. And our denominator will simplify to 3 minus the square root of 3 over 3. This 3 minus came from the fact that 1 is the same as 3 over 3. So now we can turn this into division by saying the square root of 3 plus 3 over 3 divided by 3 minus the square root of 3 over 3. We'll flip this fraction and multiply them and have the square root of 3 plus 3 over 3 times 3 over 3 minus the square root of 3. Then when we multiply, our 3's will cancel each other out, and we'll be left with the square root of 3 plus 3 over 3 minus the square root of 3. Notice that the two answers for our two different methods don't appear to be the same, but if we enter them into a calculator, we'll get the same value. This is the same value we get when we ask the calculator for the tangent of 75 degrees too. The reason the answers look different from each other is that they haven't been fully simplified. If you'll notice, there's a radical in the denominator. To fix both answers, we need to multiply the top and bottom of our answers by the conjugate of the denominator, which looks just like the denominator but has the opposite sign between the two terms. This is called rationalizing the denominator. Then we can simplify even further and see if we can make the answers look the same. Let's start with the first one. First, we need to make a conjugate version of the denominator and multiply the answer. So our first fraction is the square root of 2 plus the square root of 6 over the square root of 6 minus the square root of 2. Remember, we need to multiply by the conjugate of the denominator. So we'll make a fraction out of the conjugate of the denominator. The conjugate means that the sign in between the two terms is going to change. So we'll multiply by the square root of 6 plus the square root of 2 over the square root of 6 plus the square root of 2. This fraction simplifies to 1, so we're not changing the value of our fraction at all. Now we can use FOIL to multiply our numerators together. The square root of 2 times the square root of 6 is the square root of 12. Plus the square root of 2 times the square root of 2 is the square root of 4. Plus the square root of 6 times the square root of 6 is the square root of 36. Plus the square root of 6 times the square root of 2 is the square root of 12. Now we'll do the same thing for the denominator. The square root of 6 times the square root of 6 is the square root of 36. Plus the square root of 6 times the square root of 2 is the square root of 12. Plus negative square root of 2 times the square root of 6 is the negative square root of 12. Plus the negative square root of 2 times the square root of 2 is the negative square root of 4. Now we'll simplify our radicals a little bit. The square root of 12 can be simplified to 2 times the square root of 3. The square root of 4 is 2. The square root of 36 is 6. And again, the square root of 12 is 2 square root of 3. On the bottom, we have the square root of 36, which is 6, plus the square root of 12, which is 2 root 3, plus the negative square root of 12, which can be simplified to minus 2 root 3, plus the negative square root of 4, which can be simplified to minus 2. Now we can combine like terms in our numerator. 2 times the square root of 3 plus 2 times the square root of 3 is 4 times the square root of 3, plus 2 plus 6 is 8, over our 2 square root of 3's will cancel out here because 1 is positive and 1 is negative, and we're left with 6 minus 2, which is 4. From here, we can factor 4 out of our numerator and get 4 times the square root of 3 plus 2 divided by 4. Our 4's will cancel each other out, and we'll be left with the square root of 3 plus 2. Okay, now we'll do the same thing to the other one. So we had the square root of 3 plus 3 over 3 minus the square root of 3. Again, we're going to multiply by a fraction that has the conjugate in both the numerator and denominator. So the conjugate of 3 minus the square root of 3 is 3 plus the square root of 3. And now we're going to FOIL our numerators and denominators. So the square root of 3 times 3 is 3 square root of 3. Plus the square root of 3 times the square root of 3 is the square root of 9. Plus 3 times 3 is 9. Plus 3 times the square root of 3 is 3 times the square root of 3. Then in our denominator, we have 3 times 3, which is 9. 3 times the square root of 3 is 3 square root of 3. Plus the negative square root of 3 times 3 is negative 3 square root of 3. And the negative square root of 3 times the square root of 3 is equal to the negative square root of 9. We can simplify our roots here a little bit and get 3 square root of 3 plus the square root of 9 is 3 plus 9 plus 3 square root of 3. And then in our denominator, we'll have 9 plus 3 times the square root of 3 minus 3 times the square root of 3 minus the square root of 9, which is 3. Now we can combine like terms in our numerator and denominator. 3 times the square root of 3 plus 3 times the square root of 3 is 6 times the square root of 3 plus 3 plus 9 is 12. Divided by our 3 times the square root of 3 will cancel each other out because one's positive and one is negative. And then we're left with 9 minus 3, which is 6. Now we can factor out a 6 in our numerator and get 6 times the square root of 3 plus 2 over 6. Our 6's cancel out, and we're left with the square root of 3 plus 2. So we can see that both of our values are equal to the same thing, even though originally they looked a little bit different. And this is a much nicer number, so rationalizing the denominator can sometimes be really useful. We also have identities to find the difference of two angles rather than the sum. These are the difference identities for sine, cosine, and tangent. We use these the same way we use the sum identities, but they enable us to find some smaller angles. For instance, we could use the sine difference identity to find the sine of 15 degrees, using 45 degrees as alpha and 30 degrees as beta. Once again, we start by gathering the information we need and defining our alpha and beta angles to keep things organized and minimize the risk of a mistake. So for this problem, we're saying that alpha is equal to 45 degrees. Since we're looking for a smaller angle, our alpha has to be bigger than our beta. So beta will then be 30 degrees. The sine of 45 degrees is equal to the square root of 2 over 2, and the cosine of 45 degrees is also the square root of 2 over 2. The sine of 30 degrees is 1/2, and the cosine of 30 degrees is the square root of 3 over 2. Now we're going to write out our sine difference identity. So this says that the sine of alpha minus beta is equal to the sine of alpha times the cosine of beta minus the cosine of alpha times the sine of beta. Then we simply substitute all of the appropriate values into the formula. So we have the sine of alpha minus beta, which is 45 degrees minus 30 degrees, equals the sine of alpha, so the sine of 45 degrees, times the cosine of beta, which is 30 degrees, minus the cosine of alpha, which is 45 degrees, times the sine of beta, which is 30 degrees. So we're going to start by subtracting our values on the left to get the sine of 15 degrees, which is what we're looking for, equals the sine of 45 degrees, which is the square root of 2 over 2, times the cosine of 30 degrees, which is the square root of 3 over 2, minus the cosine of 45 degrees, which is the square root of 2 over 2, times the sine of 30 degrees, which is 1/2. Now we can multiply and simplify a little bit. So the square root of 2 over 2 times the square root of 3 over 2 is the square root of 6 over 4, minus the square root of 2 over 2 times 1/2 is the square root of 2 over 4. Since these are the same denominator, we can simplify this to a single fraction and get the square root of 6 minus the square root of 2 over 4. Sine of 15 degrees is equal to the square root of 6 minus the square root of 2 over 4. This time there is no radical in our denominator, so we don't have to rationalize it. We can check this value on a calculator by finding the sine of 15 degrees. This gives us an approximate value of 0.259. Remember, our answer with radicals is the exact value for the sine of 15 degrees. The cosine and tangent difference identities work the same way. We simply plug in our values and enjoy working with radicals until we have our answer. I hope that this video helped you better understand the sum and difference identities of trig functions. Thanks for watching and happy studying!